Thank you so much for coming. Yes, as Matt said, my name is Anton. I am a PhD student here in the IOA, working on gravitational lensing in the context of cosmology. And the point of today's talk will be to explain to you what it is that we can learn using this technique and why it helps us address some of the most fundamental questions we can ask about the universe, such as what it is made up of or what its fate is. In particular, I study the cosmic microwave background, which I will also be explaining to you later on. And I am part of a big international collaboration called the Simons Observatory, which is building the next generation telescope to study the cosmic microwave background. It's going to be placed in the Atacama Desert in Chile, and I'm going to be showing you some stuff related to that as well. So let me begin with a brief introduction to cosmology. Cosmology is defined in the Cambridge English Dictionary in this way. And I would add something to that. I would say that cosmology is the study of the origin and evolution and ultimate fate of the universe, as well as its nature. And it all began with, well, at least underwent a revolution with Einstein's formulation of gravity in terms of geometry. So what Einstein's equations tell us is that matter tells space how to curve, and curve tells matter how to move. We can begin to make theoretical progress in understanding the universe if we make one very humbling assumption. And it is that there is nothing special about our particular location in the universe, that if we smooth the contents of the universe over large scales, that it should all pretty much look the same everywhere and the same in every direction. This can be described as the universe being homogeneous, the same everywhere, and isotropic, the same in every direction. This is, of course, very different from what we experience in our daily lives. But actually, observations to date match this understanding, at least on large enough scales. So you can plug in this assumption into Einstein's equations, and it tells you that there's only a handful of possible universes that are valid. And they have some pretty funky behavior. So some have a big bang, a beginning, some have an ending, what some people call a big crunch. You get accelerated expansions, late times, early times, like there's many possibilities. So in order to be able to make some progress, we need experiments. And the first big developments in this front came in the early 20th century. Most notably, in 1929, Edwin Hubble from the Palomar telescope in California measured the spectrum from many galaxies around us. And he noticed something interesting. But before moving on to that, let me just explain what a spectrum is. So chemical elements prefer to emit and absorb light at specific frequencies, which equivalently can be said as specific wavelengths. So if you imagine you have a tube in the lab and you fill it up with a gas, say hydrogen, you shine light on it. If you then study the light coming out of the other end, you'll notice that certain frequencies have been absorbed by the gas. And if you look at its spectrum, here for example, you'll see these as gaps in its spectrum. Okay. Interestingly, we see these features in the spectrum of stars, of our own sun, of galaxies. Wherever there's hydrogen, we'll see the same signature absorption lines. What Hubble didn't measure, which was very interesting, was that these spectral features in light coming from faraway galaxies were generally shifted to the red, towards the red, the more so the further away these galaxies were. And what this means is that these galaxies are actually receding relative to us. And this has a crazy implication, which is that the universe is expanding. Okay? In order to see this, let me try a silly analogy on you. I hope this works, but it's not guaranteed. So I like to think of the universe as a loaf of bread that's rising in an oven. Okay? So these raisins, or sultanas as I think you call them here, are, imagine that they're galaxies, okay? And the dough in between the galaxies is just space between those galaxies. Right. So as the dough rises, as the bread rises, from the viewpoint of any specific racing, the other racings will appear to be, fleeing, right? But of course, there's nothing special about any specific racing. The same will be observed by an observer standing on another galaxy, another racing. Right? In the same way, in our universe, we see galaxies receding away from us, not because they actually have decided to go in the direction opposite us, but because space itself is stretching in between us. And there is a limit to this analogy, because of course the bread is rising, is expanding into the empty space around it in the oven, whereas our universe is actually not expanding into anything. It's the space itself that's stretching. It's as if more space was being created in between us and other galaxies. And of course, the recession velocity is larger the further away the racing is, because there's more space in between. Now, this again has another crazy implication, which is the fact that if the universe is expanding now, it suggests that if you could play the expansion in reverse, there would be a beginning that would be very hot and very dense. That would be our Big Bang. And of course, at first, this seemed like a ridiculous idea to most people, to most practicing cosmologists. And it wasn't until 1967 that people started to come around to the idea. And it was with the discovery of the cosmic microwave background, which from now on I'll be calling the CMB. It was discovered by Arno Penzias and, forget his name, Wilson, from Bell Labs in the United States, with this funny-looking antenna, which was initially designed to research radio communications. But they discovered that, irrespective of what direction you pointed it at, you would pick up the same signal. So they were able to come up with this picture of the sky that looked like this, and they got a Nobel Prize for this picture. Well, it turns out it's incredibly interesting from the point of view of physics, because what you're actually measuring here is the leftover radiation from the hot Big Bang. The only way that you could detect the same temperature, same temperature of radiation in every direction is if it has a common origin at early times. So this is actually a baby picture of the universe emitted when it was only 0.002% of its current age, or only 380,000 years after the beginning. The universe is now 13.8 billion years old, we think. Another, perhaps even more interesting thing about this picture is that even though it looks incredibly homogeneous, the universe in those early moments was incredibly homogeneous. There are tiny deviations from the average temperature, and if we blow up those deviations, we get a beautiful picture like this. This was taken by the Planck telescope a few years ago. So here, red regions are slightly more dense, slightly hotter regions, whereas blue regions are underdense. This here is the effect of quantum fluctuations generated during the first trillionth of a second after the beginning, and letting those fluctuations, those slightly overdense points, attract the matter around it and start clumping up. 380,000 years later, it looks like this. And if you need more reasons to think that this is beautiful, it's actually the oldest photo that we have of the universe, and it's actually the oldest photo we can ever take of the universe, at least using electromagnetic radiation. And the reason for that is that at times earlier than this, the universe is opaque, because the temperature is so high that protons and electrons are moving very fast, and so much so that they cannot combine to form hydrogen. So any light that you would hope to see from the early universe just gets immediately scattered away by free electrons. But then from this moment on, from the moment this light is emitted, light is allowed to travel freely until we receive it today. So we can simulate what would happen to those seeds of structure, to those tiny fluctuations, using modern computers. And what we get is that the seeds start attracting more and more matter, structures begin to form. At first, the universe is dark because stars and galaxies haven't formed yet, but eventually, some 500 million years in, they do. Later on in the game, our galaxy forms, our planet forms within that galaxy, and eventually us as observers are able to point telescopes back and see back in time, because remember that when we look out into the sky, we're actually seeing the past, because light travels at a fixed speed, so we're seeing objects as they were when that light left them, you know? Consequently, telescopes are some kind of time machine. So it is quite amazing that, you know, we are able to understand the universe as well as we do. Like, we can essentially come up with a model which we call lambda CDM. I will explain why. That uses just 6 parameters to accurately explain 14 billion years of cosmic evolution. It just assumes Einstein's general theory of relativity, homogeneity, and isotropy, and it just gives us all the observables that we can think of, essentially. Now, these 6 numbers are basically how much luminous and how much dark matter there is, the amplitude and distribution between large and small scales of the primordial seeds of structure, the current age of the universe, and basically the time at which the first galaxies and stars light up. And this is really remarkable, but I mean, we've glossed over the details, because 95% of the contents of the universe we don't know about. Only 5% of it, our model tells us, is in the form of stars and gas and light, like the things that we're familiar with. According to this model, which by all means seems to be correct, 70% of the energy in the universe is in the form of some strange substance, which we call dark energy, just because we have very little idea about what it is, which must be there if it is to fuel the accelerated expansion that we observe at late times. This, if it were a substance, it would be one that would not dilute as the universe expands. It could also be just a geometric factor. In fact, this lambda is the cosmological constant, which is one possible version of dark energy. And the cosmological constant, Einstein introduced already in his equations in the beginning of the 20th century. So in addition to dark energy, there's also dark matter, which we know very little about as well. It's a type of matter that does not emit light, absorb light, reflect light. It does not interact through electromagnetic radiation, but it does interact through gravity. Its presence can be felt due to its gravitational effect. So how can we begin to make some progress on understanding these mysterious components of the universe? Well, what I want to convince you of today is that there is this tool, gravitational lensing, which is perhaps the best handle we can get on the dark components of the universe. So if you had empty space, vacuum, and you shot a beam of light, it would travel in a straight line. However, if you put a mass in this space-time, space-time will curve, and then the path, the light will follow a bent path around it. The extent of that deflection will be a function of how much matter you've put in, and also the geometry of the system. And there's this nice analogy with just conventional lenses that we can draw. Just that in our case, the role of the magnifying glass, the role of the lens, is played by matter. And what's very important is that it's not just the conventional types of matter that we're used to. Lensing is induced by dark matter as well. So by quantifying the deflections that we observe, we can probe that dark component. And here, this observer is seeing the image of this light bulb magnified, because rays of light have been made to converge in the eye, we will be seeing the same sort of things with observables in the universe, with galaxies and with the cosmic microwave background. So indeed, this applies as well to everything that we observe in the night sky to different extents. So the idea, just to reiterate here, we're seeing again that evolution of structure over time, how matter clumps up due to gravity. If we were then observing from here, some background image there, the light that gets to our eyes has been deflected along the way. Therefore, the image that we see of that background object will have been distorted, right? And so in the case of the cosmic microwave background, which is what we're observing in this case, this effect can be seen hopefully in the next couple of slides. So here, just to explain what I'm showing, here I'm showing the cosmic microwave background before lensing. We can't actually go out and observe this. We only see it once, and it's after it has, the light coming from very far away has been deflected by all the matter that exists along that path. But in a computer, we can generate a mock emitted CMB without the lensing effect, and then generate a matter distribution, basically simulate a universe with its components, and apply the deflections to it. Okay. For now, in general, don't worry about these bottom two panels. I've only left them there for those in the audience who are a bit more experienced and who might know that the CMB is polarized. It has two types of possible polarization, an E mode and a B mode. And the B mode is incredibly interesting because it's associated with gravitational waves generated during the first trillionth of a second after the beginning of time. So a detection of it would be incredibly interesting, but the point is that it is kind of washed away by this lensing effect. And actually one of the most active areas of research in modern cosmology is to try to clean up this lensing B mode, to try to extract the fundamental signal. But let's close this parenthesis. And the point I want to make is that what lensing does to the cosmic microwave background is to distort it in these ways, right? So regions that lie behind a clump of matter have been magnified, kind of as if you had put a magnifying glass to it. Regions behind an underdensity or a void have been demagnified, and generally there is this distortion effect. What is very interesting is that we know the statistics of the unlensed CMB very, very well. And thanks to that, by comparing what we expect with what we actually observe, we can identify places where it looks funny, and from that reconstruct all the matter that exists in between us and it. That is, all the matter that exists in the universe. It's kind of like as if the same way that you can go to the beach and the fact that you can tell where somebody has been sunbathing because of how they have disrupted the patterns in the sand. You know what it should look like without the sunbathe there, and then you can, by telling the difference, you can reconstruct additional information. So you can actually apply this to observations from the Planck telescope, which is a space-based observatory making measurements of the CMB, and we get this very interesting picture of all the matter distribution in the universe in every direction. So here we've taken a sphere around us and unfurled it into this shape. Places colored in white contain more matter. Places colored in blue, less matter. Okay? This funny gray stuff in the center are just regions that we've chosen to discard from our analysis because, well, I say we, the scientific community. I'm not responsible for this analysis. But are regions that have been discarded because the contamination from emission from our own galaxy was just too large to deal with. So our galaxy emits very brightly in microwave frequencies. It's mostly dust that vibrates as it gets excited by starlight, and also relativistic electrons, all sorts of things that make it so that we can't really use these regions for science. So this is what Planck was able to reconstruct. There are ground-based experiments, such as the ACPOL telescope here in the Atacama Desert in Chile, which are after the same kind of science, but because they're on the ground, they're able to put a lot more detectors into their telescopes. They're able to really drill into a particular patch of the sky, measure it with very low noise levels. And so ACPOL telescope has reconstructed this. So this result is not published. You're some of the first people to see it. It was lent to me by some people here in Cambridge who were doing the analysis. I asked them if I could show it to you, and they were very happy with it. So this is a map of the matter distribution in a small patch of sky. Again, white means places where there's more matter, black where there's less matter. Overall, this is a combination of both luminous and dark matter. And what I think is really cool about this this map is that if you observe a map with the locations of galaxies in the sky, and you smooth it, okay, such that you no longer have the individual galaxies, but you have some smooth map of where there's more mass in the form of galaxies and less, and you overlay it here, you see amazing agreement. So here, the contours are this smoothed out map of galaxies. Red regions are ones with more galaxies, blue with less. And it's really amazing that you can trace the mass using galaxies, and that matches so well what you're able to reconstruct just from the deflections in that funny looking circles that you see in the CMB, right? So there's very exciting science to come very soon from CMB telescopes. As I said earlier, the Simons Observatory is being built in the Atacama Desert in Chile. Telescopes in the South Pole, which is the other main observing site for the CMB, because it's very dry, surprisingly, are going to be upgraded, and a new generation of experiment is going to be taking data very soon. Hopefully these will all merge or combine in the next decade or so to give rise to a stage 4, very large CMB experiment, for which lensing will be one of the main science goals. But just very briefly, before we conclude, I want to tell you another way in which lensing can be harnessed to extract information about the dark universe. And it is galaxy weak lensing, which uses galaxies themselves as the backlight instead of the CMB. So the idea is illustrated here, I hope, although this is an extreme example. It's still real. This is an image taken by the Hubble Space Telescope. But what I mean by extreme is that the lensing is very strong. So here, somewhere around there is a cluster of several hundred galaxies, a lot of mass in there. And behind it, there are several hundred other galaxies. Because the lensing is so strong, the image from these background galaxies has been lensed to give rise to these arcs that you see around here. In reality, there's only a handful of such combinations of clusters and galaxies in the background, such geometry arrangements that give rise to this strong lensing. So we can't really use it to map out structure in every direction in the sky. What would be really interesting is if we could use a weak version of lensing, not as strong as what we're seeing here, and use it to measure smaller distortions but over the entire sky. So the idea is perhaps illustrated better with this toy example. So imagine that you have a background distribution of galaxies, okay? And there we're assuming that they're circular. That's not true, but it will be useful for our purposes. Now place a blob of matter between this background source and us, and the image that we see from these galaxies will look something like this. the standard nomenclature in cosmology is that these galaxies are being sheared. So sometimes galaxy weak lensing, or some aspect of it, is called galaxy shear. Right. If we introduce some more realistic shapes for the galaxies, then it becomes a bit more difficult to tell where the lensing effect is actually taking place and where it's just like intrinsic distortion, where we're just seeing something interesting in the intrinsic shape of the galaxy. But so what we would like to do is to measure the shapes of these galaxies and extract from it what component is due to gravitational lensing distortions. If we were to look at only individual galaxies, this would be exceedingly difficult. So for one, we don't have a good understanding of the intrinsic shapes of galaxies. And when we observe a galaxy, we observe it after it has already been lensed. So you're trying to then distinguish its intrinsic shape from the distortion due to lensing, and the distortion due to lensing is generally very small, 4 to 3% or so. It doesn't help that when this light coming from this galaxy enters the atmosphere, and when it enters our telescope, it gets blurred out. Furthermore, if there were two galaxies along the same line of sight, those images would blend, it would make things more complicated. Then an essential part of any observing process is that you're going to pixelate the image, and then there's the inevitable experimental noise added on top of it. And at the end, you're trying to, tell this tiny effect due to lensing using this image. So it's obviously probably impossible, but you can benefit from averaging over the distortions to many millions of galaxies. You're looking at the correlation in the shapes between many millions of galaxies. What I mean by correlation is kind of the extent to which you can predict the shape of a galaxy just by looking at its neighbors. But this is, as you can tell, it's an incredibly difficult measurement, and that's the reason why, even though the theory for this was laid out in the 60s, it wasn't until the year 2000 that the first measurement of galaxy weak lensing was made. It requires very, very powerful telescopes making measurements of millions of very faint galaxies, determining their redshift with great precision, measuring their shapes also with great precision. And it's only now that we can really extract precision constraints on cosmological parameters and dark energy, dark matter from it. So these are the 3 state-of-the-art surveys at this time. Their cameras mounted on some of the most powerful telescopes on Earth. The HSC, the Hypersuprime Can, is mounted on top of the Subaru telescope in Mauna Kea in Hawaii. The Dark Energy Survey and the Kilodegree Survey are both in the Chilean Andes. You can do similar things as what we were looking at for the CMB. You can use it to map the projected matter distribution in different directions in the sky. Again, here, red means more matter, blue less matter. But what's really cool and unique about weak lensing is that you can do this for different times, essentially. So this is called weak lensing tomography. The idea is that for every galaxy that you have in your survey, you have a redshift, which tells you more or less the time at which this galaxy exists, right? So you can group them into bins. You have groups of galaxies which are at different times. You then study how lensed those galaxies are, and each of those groups will only be responsible. Each of those groups, suppose take this one, will only be lensed by the matter in this other group, right? So in this way, you can get a handle on how much lensing there is at different times, how clumpy the matter in the universe is at different times. And this is actually super useful to study dark energy. The reason is that dark energy, which we know kicks in at late times, tends to rip the universe apart. And in doing so, it kind of plays an opposite role compared to gravity. It tends to inhibit gravitational collapse of things. So by measuring how stuff is growing, the growth rate of structure, you can infer what kind of role dark energy is playing. But this whole procedure requires very, very precise measurements of the redshifts of the galaxies. And fortunately, if we are now here, these are the experiments operating now, there are plans to build much more powerful telescopes, which will come online quite soon, which should really bring down the errors in this whole procedure down greatly. And in this case, they will begin to survey billions of galaxies. For LSST, for example, these billions of galaxies will be spread over half of the entire sky. LSST is observing from the southern hemisphere. And Euclid and W1st are going to be observing from space. It's very exciting times for this kind of science. So just to conclude, I hope I've motivated why I think that we can extract very interesting physics from CMB lensing and galaxy lensing, both individually and in cross-correlation. And that it's a great time to be doing this type of work because there's many very interesting experiments being built. But perhaps the most important point that I want to make today is that even though we've made great progress in the last century, the most important questions, the biggest questions remain unanswered, and perhaps it's some of you younger folk in the audience who will be responsible for explaining them to us. Thank you very much.